do the attendance before we get going. Okay, your notes should include some of these concepts here. There were 2 videos, right, that I posted. And so the big idea here is we're going to make a distinction between theoretical, in theory, what should be happening, and experimental probability. So what actually did happen, right? And they're not always the same, okay? But if you, for example, let's do cards, right? Drawing cards. There's a theoretical probability of drawing a red card, right? A deck of cards has half of them are red, half of them are black, right? So the theoretical probability is that one out of every 2 cards should be red. Same with black, but one out of every 2 should be black. Let's put it this way: diamond, right? 1 out of every 4 cards in a deck would be a diamond, right? Because it's a full suit is diamond, right? And so in theory, if you draw 4 cards, you should be getting 1 diamond in there. But it doesn't always translate to reality. You would have to do that for a number of times. Like you would have to increase what we call the sample size. The sample size is key here. That's a word that you're going to hear me say over and over again, or 2 words. Sample size is the amount of times you try something, okay? And after a long time, that is actually the experimental, what you're actually doing, and the theoretical are going to start matching. They're going to get closer and closer together, okay? And then there are certain things that you just cannot, there's no theoretical, it's only experimental. For example, the blood type. Like humans and blood types, it's just a fact that there are certain blood types that are more common than others, right? So you can't say if you have 10 people that, you know, that there's a probability of one person having a certain one. We go by experimental. What do we observe in the world? What do we observe? Well, most people have a certain type of blood types, right? So then we're going to make a distinction between them. So I'm going to go back and forth and ask you, do you know which one applies in this certain scenario? And why are they not the same, right? So you'd have to say, well, it hasn't been done enough. The tries haven't been big enough to match, right? And also probability can be stated as a fraction, decimal, percent, and in words, okay? And so then after we talk about probability, we're gonna go between probability and odds. Odds are different. Like odds, you will see it could be events in favor to events against, right? So you put that colon in between. That's how you state odds, right? Probability is, in a sense, and write this down in your booklet, probability, because that's at the end, you're going to look at it and it totally makes sense, at least if you're following the lessons, right? Probability is always the favor over total, whereas odds is favor events in favor or against. And we can flip that later, okay? You can flip that later and you'll see how it changes over time, okay? And I'm just briefly going to go through this, what you should have seen in your notes, right? I think I went over simplifying fractions and how to do that. You have a calculator at hand. But the main idea of simplifying fractions is that you divide both the numerator and denominator by the same value to get a smaller fraction. They're still the same, but it's reduced, right? You don't have to worry about reducing a whole lot. Maybe from time to time I'll make it appear on an AC where I ask you to reduce the fraction. Okay. And so here, let's go to this table on page 145. I extended it so you probably don't have these values in there. If you didn't take the notes, it's not going to be there. I added this part here. Okay, So we basically went from a fraction to a decimal to a percent, right? And we filled in this table, okay? One thing that I want to tell you is that I don't want you to round decimals that are finite. What does that mean? Well, it ends. Like if you only have on your calculator 0.125, keep it like that. Don't round it to 1.3. Okay, I would say just keep it at 0.125, and you go from there. Okay, and once you get your decimal, you can get to a fraction, and that fraction, when you reduce it, gets you to 1/8. And how do I get from the decimal to the fraction, you may ask? I always count a number of decimals. Like if there are 3 decimals, right? After the decimal, you count the places. There are 3. That's how many zeros will be down here in the denominator. So you copy down that whole decimal up top, followed by 3 zeros, 1 and 3 zeros, right? And technically, if you stated that, you'll be fine. That it would be all I needed for the fraction. And then normally when it's not COVID times, I would ask you to also reduce, but I'm kind of letting go of that a little bit because that's not as important as me knowing that you can go from a decimal to a fraction, okay? That's what's important. And then I added, for example, the 3/7. This is what I would have added in your books. And I went from there to a decimal. Notice that when I wrote it as a decimal, how do I do that? I go 3 divided by 7, right? Just making sure it's Friday, right? We're like, how do I do that again? I don't want to think today, right? And notice that I round to 4 decimals, 4286. Write this down, right? We do 4 decimals in this unit. And I'll tell you why, because when you go from the decimal to the percent, we just basically multiply this by 100, right? If you multiply a decimal by 100, you get the percentage. When you divide it, you get the decimal. So I want you to be sure you do that. Here I went from there. So if you want to put arrows down, it's like it started here and I went from there to there, right? And notice that it's 4 decimals. So I added 4 zeros down here. That's how you go from a decimal to a fraction. And here I believe I started with my decimal and I went there and then I went there. Okay, I went times 100 here, just so you know how I get to there. That should be fairly straightforward. And then it's 2 decimals, so it's going to be 1 followed by 2 zeros in the denominator. And so this would be fine with me. This would be okay with me here. So not having to reduce is you'll be fine. You'll survive if you don't know how to reduce a fraction. Okay, so I'm kind of just going through the things that were talked about in the video. So if you need a bit more detail, you go ahead and do that. So you should have filled in this table as part of your work. And obviously the printed ones were already there. So in this case, you get your decimal, you times it by 100, you get that. To write it as a fraction, you just go 89 over 100, done. Okay. Then here you were given you started here, you divide it by 100 to get to the decimal, and then you just rewrite it as a percent like that. You can't even reduce those any further. Okay. Then you started with a fraction. You go 2 divided by 37 gives you this, and this is rounded to 4 decimals. Keep that in mind, 4 decimals. And then I multiply that decimal by 100 to get 5.41%. Here I'm giving a decimal in the middle. Watch what I did, times 100 to get there. And it's 3 over 100 because there are still 2 decimal places after the decimal. And so forth. Like this just was just repetitive. Again, watch the videos to get the full experience. I sound just as boring as live. Okay, so it's nothing fancy. It's just me recorded. Basically, what I did before. Those that watched the video, I'm just gonna pause this here because I feel like I made. Way to go, guys! You actually did it. That's always a problem. Like students think, oh, I've got all this time to do it, and then it never ends up happening, right? But I'm thinking this is where you show initiative, right? For this is a grade 12 year, right? We're going to talk about experimental probability here a little bit. And notice that some of the definitions, they appear here and as well on the side. So it's a little repetitive. And this I already mentioned on the previous page. Okay, Griffin, page 146 in your booklets, okay, probability booklet. And here's what I want to talk about. Probability is a prediction of how likely it is that a particular event will happen, okay? And this is the formula. Probability of something happening, just don't think of this as anything intimidating. It's just like the probability of you drawing an ace, for example. Think of it that way. Is the number of aces over the number of total cards that are in a deck, right? And it says here probability is expressed in lowest terms, but that we won't apply that this semester, okay? This is going to be so important, this concept right here. What in the world is that saying? Well, the probability of something happening and the probability of that same event not happening is always equal to 1 if it's decimals, if you're stating it as decimals, or 100%. So for example, if the probability of it raining today, we're going to have wet, snow, or rain mix, right? If it's 40%, if they tell you that the probability of raining today is 40%, then you know that the probability of it not raining, this is how we do this in math, like we put a little bar over it or sometimes a little tick on the side here. We know it's going to be 0.6. And together, they add up to 1 or 100%. So the probability of it raining is 40%, not raining therefore is 60%. So that's how you have to understand probability. That something happening also has its not happening counterpart, okay? Experimental probability is calculated based on measuring occurrences. Can you highlight that? I don't think I did in my original. Experimental probability is calculated based on measuring occurrences, so actually trying it out. I'll put this down here. Actual trials, right? I'm sure that in elementary, right, you did a lot of dice rolling and you probably kept track of what you got, like your teachers got you to do that. So yeah, that's experimental. You're trying to find out if the theoretical matches the experimental. And then using the results, you can make predictions of likelihood of future occurrences. Example, election polls. Okay, when they say, hey, Trump and Biden, right? Like that's everybody knows Trump and Biden, right? Like there were polls, right? And so they're like 45% are in favor of Biden and 40% are in favor of Trump, right? How do they know that? Did they ask the whole country? No, they ask a very diverse, spread out group of people, and maybe just 1,000 or maybe 5,000 people, they just ask random people all over the country, you need to make sure you're diverse across the ages, different parts of the country, right? And they collect that and they're like, well, we have a pretty good sense of this, and you study for that, right? Doing polls is extremely difficult, right? Doing it well. And so they say, okay, now we can predict that this is going to be representative of the whole country, right? So they take a small experiment, right? A small sample size, and they apply it to the whole population. Okay. So we're going to continue here. I'm just going to flip through what I had for you. I think I stopped with the blood types, correct? Anybody in here? Where did you end up with which page? Was it 149 or something? Or where do you start having a blank? You can have 149. Did I cover 149, Amari? Yeah? So 150 would be new to you. Sizes. Very important. Okay. So I will ask you to write down on the side here sample size so that it sticks out, right? Make sure I noticed a lot of you when you wrote your cum, I didn't see evidence of you going back. Sometimes, like a lot of you did go back and check your notes, but some of them were basic vehicle finance questions, and I saw mistakes that could have been prevented. Okay, so make sure you stay on top of this and you go back and review when there's a cumulative, right? All right, when performing an experiment to calculate experimental probability, you need to consider the sample size. There it is again. When you have an experiment or some kind of trial, you have to consider the sample size. That is the total number of objects or events being counted. So you're worried about the total number of objects being counted, right? A small sample size may not give the results that are representative of the whole. Okay, a small sample size, okay, may be inadequate, will not give results that you want that are representative of the whole. Okay, when the sample size is appropriate, the probability of the event of interest will be the same. Okay, when the sample size is appropriate, okay, the probability of the event of interest, probability in the sample size will be representative of the whole. Okay, so there's a lot of stuff in there that is very important for you to understand, right? So asking people, by the way, okay, like if you call people, if you actually call to ask, hey, what's your favorite candidate, or who would you vote for? If you just call people, would that be a good sample size? Just calling people? When is the last time you picked up a 1-800 or unknown number? I don't pick them up. Or even if they do, it's like, I don't have time, sorry, but right, you just hang up on them. Try not to be rude, but anyways. So calling people would not give you a good sample size. But now if you text or if you have like some kind of online platform, Facebook, right, social media, if you collect your data there, you got to be careful because the ages, right, the age group, they know which age group to get information from. Okay, so there would be a problem there. Okay, so let's look at these examples here. A large cafeteria that serves lunch to more than 400 people per day offers 4 main dishes: spaghetti, hamburger, chicken chow mein, and vegetarian dish. Of the first 10 people, so 400 people is like your whole. That'd be right, the whole population, so to speak, in this case. Of the first 10 people through the line, no one chose a vegetarian dish, right? No one chose a vegetarian. The manager decided to remove vegetarian dishes from the menu in the future. Is this a good decision? Explain your answer. It's a terrible decision, right? You shouldn't be a manager if that's how you make your decisions, right? But you would have to say something like this: no, the sample size, that's the key word that I would like you to use when I ask you a question like this. The sample size of 10 people is too small, right? Basing your decision on 50 or more, sorry, what happened there? I combined or and more, or more would be more accurate. I would maybe say even 100, right? A quarter or something, I don't know, but you would definitely have to increase. In short, you would have to increase your sample size. The sample size is not adequate, increase it to be more accurate. All right, Logan, we're on page 150 in your booklet. Okay, so that's important here. Something like this. The sample size is too small, it's not accurate, you would have to increase your sample size. That's what I'm looking for there. Those are the key words and the concepts I'm after. Don't be writing a whole essay there. Just make a note of the sample size and whether or not it is appropriate. Question 6. Katja lives in Vancouver, BC. She conducted a survey in her math class and found that, so there's a survey, found that 29 out of 30 students had brown eyes. She concluded that approximately 97% of the population of Canada, that's your whole, right, has brown eyes. Is this a logical conclusion? Explain your answer. Again, it's not, right? Because you're only asking like out of 30 people, right? That is not accurate. The conclusion is not accurate. She is basing her decision on a very small sample size. Canada has what? 30 plus million people, and you're only going to base it on 29 in your class, right? Like that's just not, it's not an appropriate sample size. And so how did she come up with a 97? It's 29 divided by 30, right? That's 90.96 repeated. So that's where you got the 27 from, okay? The 97. So in case you're wondering, is approximately 97%, right? And I think you get it after that. So I'm going to move on. I'm not going to keep. They're going to give more and more of those. So where do I add this? I'm going to add that. I want to add this somewhere where it sticks out. Maybe down here. Just sample size needs to be significant sample size. So it needs to be a significant sample size that you're targeting, and it needs to be diverse, right? So I would box this in maybe. Otherwise, it is biased. Okay, that's the word. It's skewed or it's biased if you don't, if that's not the case. Okay. Practice your skills. Yeah. So I'm gonna talk a lot today, okay? Because I need to kind of rein it in. And even though I would like to give you some class time to do some work, I will just keep going through the notes, okay? So just continue following. Just in case I need to make a reference to it, go find this deck of cards. It's a gray cardstock. You cannot miss it. If you picked up the handouts, if you don't have it, then you need to come in here at one point and pick up the handouts. So who did I have? Logan and Havana and Griffin. Okay, I'm going to update that. And then I want you to find this one as well. This handout right here. Theoretical and experimental probability. I may or may not get to it, but I want you to find the deck of cards handout and this handout right here. You should have 2, 4, 6, 8, 10, 12 handouts. We will probably not use them all. I'll probably only use about 8 of them, but I decided to give them all just in case. Okay, so have that ready to go. And let's start with the practice your new skills here. Okay, have a calculator ready. I mean, 3/4, I know you know how to do that. I know, so don't give me that this is redundant. Just follow me, okay? So you write down up to 4 decimals. In this case, there aren't, you don't have 4 decimals. Percentage, multiply that by 100. So you get 75, and the kicker here is you need to add the percentage symbol there. And then words is 3 out of 4. That easy. Just go to the fraction. It's 3 out of 4. Or you could say 75 out of 100. That would also work. Okay. So that's that. Decimal, you can go this way or you can go back. I'm going to go back first. How many decimals do I have? 1, 2, 3. That means that I will write down 58 over 1 followed by 3 zeros, right? And then you have that. And I will not reduce it today. I'll just leave it at that. If you know how to do that, you're fine. Percentage, you type that in and you just multiply that by 100. And notice what happens. The decimal basically shifts 2 spots. It goes 1, 2. So it's 5.8%. There's nothing else left. And this would be, I will use the words, I'll base it on the fractions. 58 out of 1,000. Base that out of the fraction here. It's going to be easier. Okay. Now we're going to go from words and we're going to go left. Okay. Or you can go straight to the fraction. Why not? 24 out of 52. Sure, we'll do that. Okay. There it is. And then to get, this is the kicker here. Once you go from here to the fraction, I'm going to continue with my fraction. So I'm going to go 24 divided by 52. That's 0.4615. 4615 rounded. So 0.4615. And then you multiply that by 100, 4615. And that's your percentage, okay? What do you do here? I would say divide it by 100. So you take the 74.5, right? To go from here to here, you divide by 100. To go from here to here, you multiply by 100. Okay, that's how easy it is. So you divide that by 100, you get 0.745. There are only 3 decimals, so that's what it is. Okay. And then we take this and we go 745 over 3 zeros, right? So that's over 1,000. And that's it. We're going to leave it at that. And then we go over here and just say, what would this be in words? 745 out of 1,000. Done. How do I go from here to here? Top divided by bottom. Just think of it. If you graduate, right, you're gone. You're out of high school, right? The symbol that looks like a fraction is this one, is the division, right? Number over number, okay? So that should do it for you to remember that you have to divide top by bottom, and that's 0.3091. This 0 bumps up to a 1. So 3091. Then you multiply that by 100, and you get 30.91. Okay? Percent. And then 17 out of 55. There's your table filled in. I can guarantee you that there'll be an AC or more where this table needs to be filled in. Okay, so you better know how to do one of those. I don't know if you want to copy one of these, like one row into your study sheet and show what you did to go this way or the other way. Okay, keep going. 152. Let's see if you understand probability here. If 75 out of 87 beads in a box are white and the rest are multicolored, what is the probability of choosing a multicolored bead from the box? Okay. This is what they want. Probability of choosing a multicolored bead from a box. Write your answer as a fraction, decimal, and percentage. So let's try to understand this. 75 out of 87 are white. This is the total amount. Okay, this is how many you have. So if 75 are white, how many are multicolored, you might ask, right? So we'll do this. Multicolored would be 87. That's the total minus the 75 that are white. And that would give you 12 beads. 12 are multicolored. You went total minus white, right? Total white. 12 beads are multicolored. So probability, this is where I use the letters of the bead being multicolored, would be 12 out of the total, which is 87. That's my fraction. you go like this, comma, to get the decimal, you go 12 divided by 87. You get 0.1379, 0.1379, 4 decimals, right? 0.1379, comma, to get the percentage, we're just going to take that number and multiply it by 100, and that's 13.79. 13.79%, or 12 out of 87. So we went fraction, decimal, percent, and words. So the multicolored beads were not given. So bring an arrow down, because we needed that outcome that we wanted there. Can we just add on the side here? If they had asked for the probability of white marble, a white bead, that would actually be 75 out of 87. And what do you think these two probabilities would add up to? Probability of multicolored and probability of white? You would actually have 87 out of 87, right? So that would be 1. So it's basically probability of multicolored and probability of not multicolored, which is white. There's only 2 options in this case, okay? But this is what they focused on, okay? Number 3, a sports equipment manufacturing company is producing basketballs. When 276 basketballs were tested, 3 were found defective. They had a problem, okay? What is the probability that a basketball chosen at random will be defective? So probability of defective, I'll actually write it like this. Probability of this happening would be 3 out of 276. That's it. But I will do this. I'll write it as a decimal and fraction. I know they don't ask for it, but I'll go top divided by bottom. That's 0.019. 0109. 0.0109 rounded. If you multiply that by 100, you get 1.09%. You should be comfortable going from the fraction to decimal to percent. If a store buys 5,000 basketballs, how many are likely to be defective? Here, folks, you are making a prediction. Based on a smaller sample size. Okay, so you might ask yourself, is this an appropriate sample size that was used? I would say yes. 276, you pulled 276 basketballs and you tested them. That's a significant amount, right? You're not just testing 10 or 20 or 30. Significant amount. Significant amount. 276, okay? So this is how you make a prediction. Prediction, this is basically a formula, is the probability of the event happening times the, I will say, total. This is going to be my total here. Probability of that happening times the total. So we're going to go, what's the probability of them being defective? It's 3 over 276. Put that in brackets like that. We're going to multiply that by, in this case, 5,000. That's how you do these types of questions. If I ask you, for a probability, and then it's like, well, how about now if you made more of them, or if you asked more people, what would you think the outcome would be? And so this is how you enter this into your calculator. 3 divided by 276, hit equals. That's this. Leave it all in your calculator and just go times 5,000. And so you get 54.34, and that just keeps going. So approximately 54, you have to round to a full number here. 54 defective. And I'll just leave it at that, or else I'll use up too much room. I'm sorry that I used up so much room, but this is what I think this is what I would like you to have on your study sheet. This formula right here. It's not on your formula sheet, but that's how you make a prediction of something. Okay. Told you I was going to talk a lot, right? Mary flipped a coin 30 times. The coin landed on heads 12 times and on tails 18 times. That's a bit of a duh question, like, right? Like if it lands on heads 12 times, of course the other 18 times, because this adds up to 30, right? But they give it to you anyways. What's the experimental? Why do they mention that word? Experimental, because it was flipped. So that actually Mary was performing experiments, right? This is trials, right? Trials / experiments. Okay. What is the experimental probability that the coin will land on tails? Right? So we have to say probability of tails. We can actually write it like that, right? Is 18 out of 30. Let's write that as decimals as well. 18 divided by 30 is 0.6, or 60%. Wait a minute. Last time I checked, it's a 50-50 chance, isn't it? Right? Flipping a coin, that's a 50-50. It's 60. What's going on here? Well, we'll get there. Based on these experimental results, how many times would Mary expect the coins to land on heads in 600? This is the total. And they say based on experimental results. Right? We know this should be 50%, but based on this experiment, what would you say would happen over 600 coin tosses? So I actually want you to write down prediction is going to be 18 over 30. That's the probability of, oh, sorry. Yeah. I almost fell for it. Don't write this down. You're going to have to erase, because it says probability of landing on heads, right? And we know that back there it's 12. So we're going to put that 12 in there, not the 18. Sorry, my bad. So this wasn't asked of you back up there, probably on purpose, right? So you just multiply, you just go 12 divided by 30, which you know will be 40%, right? Because if tails is 60, then heads would be 40. So 12 divided by 30, you get 0.4 times 600, you get 240. 240 should or will land on heads. And this is based on the experiment. Very clearly, it's based on the experiment, right? That's what they wanted you to do. Because in theory, this is 50-50, right? Yeah, I'm going to do that here on the side. So make a little box here on the side. The theoretical probability of heads, probability of heads would be 1 and 2 or 50%. Probability of tails would also be 1 and 2 or 50%. What should happen? And you should make note that this is only based on that experimental probability. Would this be accurate? It would not be accurate. Why, you may say? Because the sample size is too small. You only flip 30 coins. You should probably flip at least 100 times or something like that. And then you would see that it's very close to 50-50. Okay? Very close to 50-50. I'm just looking at where we're at. Question 5 on page 153. A teacher began grading a test. The first 3 papers, that's pretty silly, right? The first 3 papers all received a grade of 95%. So he concluded that it was too easy. Right? He concluded that it was too easy based on 3 papers. Is it a reasonable conclusion? Why or why not? No, it is not. He is basing his decision on, here are the keywords, a very small sample size. If, half or more would score 95%, such a conclusion would be accurate. Or would probably be more accurate, right? It might still not be, it might just be that the whole class studied hard, right? Okay. Elections for a student council are being held at a high school of 512 students. I will highlight that, and that is our total, like the big number in this case here, total. Okay. The results of the poll are shown in the table. So, right, each candidate is up here, and you know how many votes went, or this is a poll, right? It's an experiment, and these are how many people are interested in each candidate. You can clearly tell it's not 512, right? What percentage of the student population was polled? The percentage of student population. They're not asking for probability. So what we're going to do is we're going to add up these numbers here, right? So we go this plus this plus this plus this, and you get 102 surveys. Okay, were conducted. So basically what we do is we go 102. It's just like your test, right? Your test score or any score you get, you go the score over 512 times 100, right? And so 102 divided by 512, sorry, times 100, that would be 19.92. Remember, we always round to 2 decimals. So of population was polled. Okay, so about 1/5. Okay, 20%, right? It's close to 20. So not that you need to do that. I'm just letting you know, right? If this poll is representative of the whole student population and all students in the school cast a vote, those are the assumptions we have to make. How many votes can Noah expect to receive in this election? Prediction, we will go probability of Noah getting, right? What's the probability of him getting elected times the total? Okay. So here we have the probability of Noah. You go all the way up here, and there he's got 9 out of 102 based on this experiment are going to vote for Noah. So 9 out of 102 are voting for Noah in a small scale. And then we're going to multiply that by 512. This is the total. So you base it on the small experiment, and then you multiply by a total to get your prediction. So 9 divided by 102, it equals times 512. You get 45.18 or 176. So that's what I'm going to do here, because this is number of votes, right? It's people that we're talking about. You go like this, squiggly line, about, let's say, 45 votes. Expected, right? That's assuming all people vote and there we go. How many votes can be expected to separate Juan and Zahira? Okay, so what we're going to do here is we're going to have to figure out each individual, like how many votes are expected. So for Juan, right, we're going to go prediction. What's the probability of him getting votes? Well, on the small scale, it was 43 out of 102. And we're going to multiply by 512. And then over here, we're going to have Zahira. What are the expectations? So prediction is going to be 35 out of 102. And we multiply that by 512. So we're basically predicting what the votes are expected for both, and then we're gonna see how many votes are separating them. What's the difference? So let's come up with each one individually, and that's 215.84 something. So we can write down, I would always round down, but either one is fine. Most of you will be inclined to round up because it's 0.8. And Zahira has 175.68. That's approximately 176. Difference. So this is a loaded question, right? Like You have to figure out ones, and then you have to figure out Zaharas, and then you have to subtract them, right? Like how many are separating them? And you have 40 votes of separation. That answers the question there. And oops, sorry, folks.